Morning children, I am S. Sangeeta working as a physical science CRT in KGBV committee. In the last session, we understood laws of Newton's first law of motion, Newton's second law of motion, inertia, types of inertia and momentum. In this session, we have learned Newton's third law of motion. Newton's third law of motion. Newton's third law of motion statement. For every action, there exists an equal and opposite reaction. Repeat. For every action, there exists an equal and opposite reaction. It explains what happens when an object exerts a force on another object. For every action, there exists an equal and opposite reaction. ప్రతి ఒక్క యాక్షన్ కి దానికి సమానమైన ఆపోజిట్ రియాక్షన్ అనేది ఉంటుంది. ఈ న్యూటన్స్ థర్డ్ లా ఆఫ్ మోషన్ ఏం చెప్తుంది అంటే what happens when one object exerts a force on another object. ఒక ఆబ్జెక్ట్ మీద వేరే ఆబ్జెక్ట్ అనేది ఫోర్స్ అప్లై చేసేటప్పుడు ఏం జరుగుతుంది అనేది ఈ న్యూటన్స్ థర్డ్ లా ఆఫ్ మోషన్ అనేది ఎక్స్ప్లెయిన్ చేస్తుంది. న్యూటన్స్ ఫస్ట్ అండ్ సెకండ్ లా ఆఫ్ మోషన్ అప్లైస్ టు ఎ బాడీ. Newton's first and second law of motion applies to one object, but Newton's third law of motion applies to interaction between two objects. It applies interaction between two objects. Let us do an activity. Let us do an activity. That activity is pulling two spring balances. Pulling two spring balances. Let us do an activity. This activity is pulling two spring balances. Pulling two spring balances. Take two spring balances. Take two spring balances. Now connect these two spring balances. Connect these two spring balances. Now pull one of the spring balance with some force. Pull one of the spring balance with some force. Children, observe it. What do you observe? These two spring balances have same readings. These two spring balances have same readings. According to Newton's third law of motion, when an object exerts a force on another object, the second object also exerts same force to first object. This is equal magnitude and in opposite direction. According to third law of motion, when an object exerts a force on another object, the second object will also exert force on first object. This force is equal magnitude and in opposite direction. Let us understand with an example. Take two objects. This is object A and this is object B. Object B attracts object A. Object B attracts object A with a force FAB. With a force FAB. FAB means force on A by B. FAB means force on A by B. And also object A also attracts object B with a force FBA. Object A also FBA means force on B by A. These two forces, that is FAB and FBA, these two forces are equal in magnitude but opposite in direction. These two forces are equal in magnitude but opposite in direction. These two forces are called as action and reaction pair. These two forces are called action and reaction pair. In Newton's third law of motion represents forces acting on two different bodies simultaneously. Forces acting on two different bodies simultaneously. Let us applications of Newton's third law of motion. First one is flying bird. First one is flying bird. This is a bird. This is a bird is flying. When birds fly, they push air downwards with their wings. When birds fly, they push air. They push air downwards with their wings. With their wings. And the air pushes back. And the air pushes back the bird opposite upward direction. Opposite upward direction. Thus the force applied by the wings, bird on air is action and opposite force applied by the air is reaction. These two action and reaction forces are equal in magnitude and opposite in direction. This is the action and this is the reaction. The second example is rocket. This is a typical rocket. This is a typical rocket. Rocket is fire. It releases hot gases. It releases hot gases in vertically downward direction, and the rocket lifts up vertically upward direction. Rocket lifts up vertically upward direction. Hence the forces on hot gases is action, and the rocket applies action on hot gases. Rocket applies action on hot gases, and in turn the hot gases gives a reverse force on the rocket, and the rocket flies up. Of Newton's third law of motion is swimming a fish. When a fish swims in water, the fish pushes the water back, and the water also pushes the fish with equal force and opposite in direction. The force applied by the water is moving the fish to forward.
Third law of motion. This law of Newton states that to every action there is an equal and opposite reaction. Newton's third law of motion is the relation between the forces themselves. Here, if one body exerts a force on another body, the other body also exerts a force on the first body. Both these forces are always equal in magnitude but opposite in direction. Activity. Pulling two spring balances. Let us take two spring balances. Connect them in between. Fix the other end of spring balance to a rigid support. Pull the free end of a spring balance A, that both the balances show the same reading. This phenomenon observed reveals that force exerted by the balance A on balance B is equal and opposite in direction to that exerted by the balance B on A. The force exerted by balance A on the balance B is called as action, while the force exerted by B on A is called as reaction. Other examples. Let us consider an example. If you hit the wall with a fist, even the wall hits your fist with the same force. This force can be felt as pain. If a porter lifts a heavy load on his head, load presses the head downwards and head pushes the load in the upward direction. These forces are equal in magnitude. F1 is the force applied by the load on the head. F2 is the force applied by the head on the load. Some more examples explaining action-reaction pair. Let us see some examples which explain action-reaction pair in Newton's third law. When the birds fly, their wings push the air downwards, which is considered as action. In turn, air pushes the wings upwards in opposite direction, the reaction. Both the forces are equal in magnitude and opposite in direction. When the fish swims in water, fish push the water back and water pushes the fish in opposite direction. Both the forces are equal in magnitude but opposite in direction. Activity. Balloon rocket. Take a balloon and inflate it. Place it on a straw and thread arrangement and tape the balloon. Ask your friends to hold the thread on either side of the straw. Fix the balloon to the straw with a sticker tape. Release the air from inflated balloon by holding its neck part. We can observe that air escapes out of the balloon, but it does not move from the place. But let us perform an activity when the balloon is free. Inflate the balloon and tie its neck. Balloon is tight as air inside it exerts force on the walls of the balloon equally in all directions. When the neck is released by removing the thread, air escapes in one direction, but balloon moves in opposite direction. That is, while escaping, air exerts net force in the opposite direction, causing acceleration in the balloon.
Conservation of momentum. Conservation of linear momentum. Take two marbles. Take two marbles with masses M1 and 2. Take two marbles with masses M1 and M2 traveling with velocities U1 and U2 with respectively. Two object masses are M1 and M2 and their velocities are U1 and U2 in the same direction along a straight line. Here, if U1 is greater than U2, if U1 is greater than U2, the two marbles are collide each other. The two marbles collide each other. The collision lasts for some time T. The collision time is first marble exerts some force on second marble. The first marble exerts some force on second marble, that is F21. That is F21. At the same time, the second marble also exerts same force on first marble, that is F12. That is F12. After collision, the velocity of first marble is V1 and the velocity of second marble is V2. After collision, the velocity of first marble is V1 and the velocity of second marble is V2. Repeat, the mass of the first marble is M1, velocity is U1. Mass of the second marble is M2, velocity is U2 before the collision. After collision, the velocity of the first marble is V1, velocity of the second marble is V2. F21 is the force exerted on first marble on the second marble. F12 is the force exerted on second marble on the first marble. Find the momentums of marbles before and after collision. First of all, this is marble 1 and this is marble 2. Momentum before collision. What is momentum? Momentum is the product of mass and velocity. Momentum is product of mass and velocity. In marble 1, before collision, momentum of marble 1 is, mass is m1 and the velocity is u1. So marble 1, momentum before collision, marble 1 is m1 u1. Next, marble 2. Momentum before collision, marble 2. Here the mass is m2, velocity is u2, so the momentum is m2 u2. Momentum before collision, marble 1 m1 u1, marble 2 m2 u2. Next, momentum after collision. After collision, the velocities are v1 and v2. Marble 1 velocity is v1, marble 2 velocity is v2. So, momentum after collision, marble 1 is m1 into v1, that is m1 v1. Marble 2 is m2 into v2, that is m2 v2. These are the momentum after collision. Momentum after collision. Marble 1 is m1 v1, marble 2 is m2 v2. Next, change in momentum. Momentum denoted as p. Change in momentum is delta p. Change in momentum delta p. In the marble 1, change is m1 v1 minus m1 v1. m1 v1 minus m1 v1. In marble 2, m2 v2 minus m2 u2. This is the changes in momentum. These are the changes in momentum. Next, rate of change in momentum. Rate of change in momentum. That is delta p by t. Delta p by t. So here delta p is equal to m1 v1 minus m1 u1 by t. This is the marble 1. Next, in marble 2, m2 v2 minus m2 u2 by m2 v2 minus m2 u2 by t. These are the rate of change in momentum. This is marble 1 and this is marble 2. Newton's third law of motion the force exerted by the first marble on second marble is equal to the force exerted by the second marble on first marble. That is, hence F12 is equal to minus F21. F12 is equal to minus F21. F net is equal to, we know F net is equal to delta P by delta T. We know F net is equal to delta P by delta T. Hence we get delta P1 by T. Delta P1 means the change of momentum of first marble. Change of momentum of first marble is equal to minus of delta P2 by T. Change of momentum of second marble. Delta P2 means change of momentum of second marble. That is, here delta P is equal to P1 is equal to M1 V1 minus M1 U1 by T is equal to minus delta P2 is equal to M2 V2 minus M2 U2 by T. Both here, both sides are T. So we cancel T. Then M1 V1 minus M1 U1 is equal to minus M2 V2 minus of minus is equal to plus M2 U2. So M1 V1 minus M1 U1 is equal to minus M2 V2 plus M2 U2. This is minus M2 V2. ఇటువైపు వస్తే ప్లస్ M2 V2 గా మారుతుంది. సో M1 V1 ప్లస్ M2 V2. ఈ మైనస్ M1 U1 అనేది రైట్ సైడ్కి వెళ్ళేసరికి ప్లస్ గా మారుతుంది. సో M1 U1 ప్లస్ M2 V2. Finally, we get M1 U1 plus M2 U2 is equal to M1 V1 plus M2 V2. So M1 U1 plus M2 U2 is, from this equation, the total momentum is unchanged. The total momentum is unchanged before and after collision. The total momentum is unchanged before and after collision. Next, so the conservation of linear momentum states that in the absence of a net external force on the system, the momentum of the system remains unchanged. In the absence of net external force of the system, the momentum of the system remains unchanged. Next concept is impulse. When we see the cricket match, the fielder pulls back his hands while catching the fast moving cricket ball. The fielder pulls back his hands while catching the fast moving ball. Why the fielder pulls back his hands? Why the fielder pulls back his hands? Yes, the fielder trying to increase the time to decrease the ball's velocity. The fielder trying to increase the time to decrease the ball's velocity. The rate of change of momentum will be less, so that the force of impact of ball on hands is reduced. From Newton's second law of motion, F net is equal to delta P by delta T. F net equal to delta P by delta T. In order to minimize F net ను మినిమైజ్ చేయాలంటే మనం ఏం చేయాలి? డెల్టా టీ అనేది మ్యాక్సిమైజ్ అవ్వాలి. అంటే డెల్టా టీ అనేది పెరిగితే, స్టాపింగ్ టైం అనేది పెరిగితే ఎఫ్ నెట్ అనేది తగ్గుతుంది. సో ఇన్ ఆర్డర్ టు మినిమైజ్ ఎఫ్ నెట్ యూ హ్యావ్ టు మ్యాక్సిమైజ్ ద స్టాపింగ్ టైం. We get from this equation F net is equal to F net into delta T. F net into delta T is equal to delta P. So F net into delta T is equal to delta P. From this equation we know that the product of the product of net force and interaction time. The product of net force and interaction time is called impulse of a net force. Impulse of a net force. Impulse is equivalent to the change of momentum. This is the change of momentum. Impulse is equal to the change of momentum that an object experiences during an interaction. Object experience in the during of interaction. Forces accepted. Forces accepted over a limit time are called impulsive forces. Impulsive forces.
On an object for a short amount of time. Impulse is the measure of how much the force changes the momentum of an object. The formula for impulse looks like this. Impulse is equal to force multiplied by small time. Or in the simple representation, impulse is equal to F multiplied by small time delta t. This impulse is a measure of how much the momentum changes as a result of force acting on it for a period of time. An alternative formula for impulse looks like this. Impulse is equal to change in the momentum. That is delta p vector. This formula relates impulse to the change in the momentum of the object. Impulse has two different units. Either kilogram times meters per second, kg meter per second, or Newton times seconds, ns. Now that we can calculate impulse, we can take a look at some interesting examples of impulse in everyday life. The most notable example is the car airbag system. Airbags are in cars in order to reduce the damage to a driver or passenger during a collision. If impulse is force multiplied by time, then force is impulse divided by time. What the airbag does is increase the time required to stop the momentum of the passenger or driver. If this time is increased, then the force of impact is decreased. If the impact time is short, then the force of impact increases and may cause severe damage to the occupants of the car. Here is an example you can do at home. You and your friends want to experiment with impulse and eggs. If you drop the eggs onto a hard surface, you all know that the egg will break. The impact time between the floor and the egg is short, which means that the force, which is impulse divided by time, becomes large enough to crack the egg. If you have 4 of your friends, hold a bedsheet a few inches above the floor, and drop the egg again. The egg does not break. Why? The bedsheet increased the collision time, and as a result, the force of impact was reduced. Also ever present in sports. In tennis, whenever a ball is hit back and forth, there is impulse between the ball and the tennis racket. In football, when a ball is punted, impulse can help determine the force of the kick. If we know the contact time between the foot and the ball. In tennis, baseball, and golf, among other sports, the faster you swing at the ball, the greater the impulse you impart on the ball. The ball then goes faster or further away.